So we've seen how useful rate of change can be when we analyze real-world data using linear regression. So that was one of the questions on your quiz, was to interpret the slope. And slope is just a word for rate of change, okay, in a linear function. But I'm going to look at a different kind of a model that involves nonlinear data. And we're going to continue to explore the idea of rate of change. So from physics, we know that the distance an object travels when in free fall is given by the function d of t equals 16t squared. Okay, so the 16 is due to the acceleration of gravity. And when we studied this before, we had a negative in front. Why do you think we don't have a negative here now? Well, this is a function of, this is distance, not speed. You can't have a negative distance. So why did I have a negative before? I was measuring position. And you can, position can be on a number line, can have a positive or a negative. Like negative would be below ground, right? So when you're measuring position, it depends on what 0 is. You could have positive or negative position depending on where you're setting 0 to be. But when we're measuring distance, that can only be positive. A certain distance from where you started can only be positive. But this is really the same physics concept. Okay. So the distance that an object travels when in free fall is 16t squared. So what does t represent? Yeah, I heard some people say it. Time. And what does d of t represent? Distance. Okay, so suppose I was going to drop an object from the top of a high building, like the Empire State Building, which is 1,250 feet tall. What window would you use to graph this function? Give me an idea of a window that would make sense.
0, 12.
Okay, so 0, 12, why would you choose that? Great, so 0 is the time we let go of our object, and then we just pick a time that we think it would take less than to reach the ground. So you have to make an educated guess there. So Vincent said 12 seconds. I don't think it would take more than 12 seconds to hit the ground. And then for d of t, we said 0, because when you first let go, it's traveled 0 feet. And then you said to 1250. And that makes sense because it does not. Yeah. Yeah, that's one of those crazy things you discover in physics, that if you drop a feather and a rock from the same height, they hit the ground at the same time. Yeah. No, in general. Yep. In a vacuum, I don't know what would happen. Okay, so let's actually use our graphing calculator to graph this thing. Okay, so I want to graph 16t squared. I don't have a t button, I'll use x. So 16x squared, and then I'm going to set the window like this, 0 to 12, and 0 to 1250. Graph. Oops, what'd I do? Oh, whoops. There we go. Okay, so that's our distance traveled. Distance traveled. So let's take a picture of this so we can draw on it. Okay, what does our graph tell us about the rate of change between the distance an object falls with respect to time? Is it constant? Is it falling at a constant speed? No, how is the speed changing? Exponentially getting faster, right? Yeah, so the rate of change is not constant. It's speeding up, right? If the rate of change were constant, this would look like a line, but actually it's speeding up. It's getting faster and faster and faster because it's going further and further than a line could go, right? Because this is distance. So at the same time, say 1, 2, 3, 4, 5, say 6 seconds, it's gone much further than it would have gone if its speed had been constant. So what common term do we use when we describe the change in distance with respect to time? Yeah, velocity or speed. When you take the number of miles you've driven and divide by how long it took you to do that, you get speed, rate, velocity. So I have some screenshots here, a table and the graph. What is d of 3? Should be able to answer without using your calculator, just from these pictures. 144, yep. So d of 3 means what is the distance after 3 seconds, right? Because 3 is the input. They're asking for the output when 3 is the input, so you get 144. And what is d of 1? 16. So how far has the object traveled from t equals 1 to t equals 3? 128, yeah. How'd you get that? Mm-hmm. Yeah, so you said in 3 seconds it traveled 144 feet, but over the first second it traveled 16 of those feet. So between 1 and 3, it went 144 minus 16, 128 feet. So we would call this the net change. So this is a word that your homework uses. When it asks for the net change of a function, it's asking you to do that. Subtract the y values. How would I calculate the average speed from t equals 1 to t equals 3? How fast was it traveling on average? No ideas? Because the equation gives you distance. It's not an equation for speed. If you were driving along on the highway, how would you calculate your average speed if your speedometer was broken? Ryan? Yeah, so we will do change in distance, right? Change in distance divided by change in time. This is speed. It's average speed, right? Not instantaneous. Your speedometer can give you instantaneous speed, but if that were broken, you could calculate average speeds by figuring out how far you drove divided by how long it took you to get there. So we're going to do the same thing for this falling object. Figure out how far it fell divided by how long it took it to fall. So this is 128 feet it fell, right? How long did it take it to fall 128 feet? 2 seconds. From 1 second to 3 seconds, it's 2 seconds. So I get 64 feet per second. On average, it's falling 64 feet per second. All right, see in your groups, work in your groups, come up with the average speed from 3 seconds to 4.5 seconds. All the information you need is in the tables on the screenshots on the page. Okay, so what is D of 4.5? 324. And what's D of 3? 144. So what is my change in D? 180. 324 minus 144. Okay, so I got my change in D. And so to calculate average speed, I'm going to calculate change in D over change in T. 180 over, what's my change in time? 1.5 seconds. So this is feet, seconds. So what does that come out to? 120 feet per second. So you see that's much faster than the average speed from 1 second to 3 seconds. Does that make sense? Should it be faster? Yeah, because objects accelerate as they fall. They move, they go faster and faster and faster. Which is why dropping something really small off a tall building is dangerous, right? If you drop a penny off the Empire State Building, even though it's really small, it speeds up and speeds up and speeds up, and it's going really fast by the time it gets to the ground. So in general, we calculate average speed or average rate of change. So if the things you're measuring aren't distance and time, but you know, number of toys you can make in a day or something, if they're not distance and time, instead of saying average speed, we call it average rate of change. So you can just call it a rate rather than speed. So we take the distance with respect to time as time changes from t equals a to t equals b, which would be change in d over change in t. Or, since we're going from a to b, we could say, well, this change in d we calculated by subtracting the two d values. So we have d of b minus d of a, that's how you calculate change in d, over b minus a, which is how we calculated the change in t. So this is exactly what we did in the last two problems. We're just writing it out in symbols now. So 64 feet per second, when we calculated the average speed from t equals 1 to t equals 3, we got 64. That's a slope, right? We did d of 3 minus d of 1 over 3 minus 1. D of 3 and D of 1 are y values, right? And 3 and 1 are x values, or D values and T values, output and input. This is a slope. That's how we normally calculate slope, between the point 1 comma D of 1 and 3 comma D of 3. Exactly. It's like y1, x1, y2, x2, y2. So that's how we calculate the slope of a line. So this thing must be the slope of some line, and it is in fact the slope of what we call a secant line. If we plot points on the curve at 1 and at 3, if you draw a straight line through them, the average rate of change is the slope of that line.
What did you call it?
It's called a secant line. Yeah, I didn't write it down here. It's just the line connecting the 2 points. It's called a secant line. So average rate of change is calculated the same way you calculate slope. It's the slope of the line connecting the 2 points you want to find the average rate of change between. So in general, we're not always working with distance and time. Average rate of change you can find by doing change in y over change in x. And the way you calculate change in y is you calculate your two y values, which would be f of b and f of a, subtract them to get your change in y, and then subtract your x values, b and b minus a, to get your change in x. And I should say, because your homework asks you some questions, net change is just the change in y. F of b minus f of a. So net change is just the change in y, and the average rate of change is when you do change in y divided by change in x. Okay, so we have two frogs, Frida and David, running a race. These graphs give their distance over time. So this is how far they've traveled at various times. So I want you to discuss in your groups. Try to come up with the answers to these questions I've asked you about Frida and David's races. Okay, so how many hours was the race? 5 hours. Who won? Ty, can you explain how you know that?
Because the average rate of change showed that even though David slowed down for some food in the middle there, he still caught up enough for them to end up at the same place at the same time.
Yes, okay, so they finished at the same place at the same time, right? They both went 5 miles in 5 hours, so this is a tie. So what was the average speed of each frog over the course of the race? 1 mile per hour. They both had a change in distance over change in time that was the same. Change in distance for both of them, they went 5 miles over 5 hours. So they were both traveling 1 mile per hour on average over the course of the race. But let's look at the average speed for each frog over the first 2 hours. So let's see, Frida, do change in distance over change in time. So over 2 hours, Frida, how far did Frida travel? 2 miles, yep. So Frida went 2 miles in 2 hours. So she was going 2 miles per hour on average for the first 2 hours. But then David, over 2 hours, traveled how far? About 2.5 miles over 2 hours. So, oh yeah, sorry. 2 over 2 is definitely 1. Thanks. And then David traveled 2.5 miles over 2 hours. So his average speed is 1.25 miles per hour. So he, on average, was traveling a little faster than Frida over the first 2 hours. So what was each frog's strategy? Yep, great. Frida had a constant speed, slow and steady. And David went fast and then slowed down and rested and then went fast again. So some people, I heard people saying the tortoise and the hare. Who would the hare have been? Right. David would be the hare, right? And Frida would be the tortoise. Slow and steady. Although slow and steady didn't win the race, it tied the race, right? Good.